Good evening. Can you hear me? So yeah. So as yesterday, I'd start class at 7. Till then, if you have any questions from yesterday, you can ask. Please. Right. So yesterday I forgot to mention one thing. So let me just start with that. So I forgot to mention the rational root theorem. And this states that if Px is a polynomial like so, where all the coefficients are integers, where ai belongs to the set of integers for all I belonging to 0 till n, and if p over q is a rational root, so obviously p and q are integers. Then you can say that q divides a n, and you can say that p divides a 0. Is this correct? So an immediate corollary is for monic polynomials with integer coefficients, I hope the spelling is correct, roots are either integers or irrational. This is easy to notice because if a monic polynomial had a rational root p by q, then q would divide 1, and only 1 and minus 1 divide 1. So p would be an integer, p over q would become an integer. Fine. This is the result I forgot yesterday. Okay, now let's wait for 7. No one else can go until then. Then we start with combinatorics. And it's nearly 7, so let's start. Okay, let's try to finish it with time left today instead of going over time like yesterday. So I won't mention the rules, but I hope all of you know the addition principle. I won't write them down. And so addition principle and multiplication principle, you should know both of those. I mean, you subconsciously know them, but yeah, so Should know the name, I guess. That's what they're called. I won't mention them any further. Then there are some basic formula like NPR is equal to n factorial over r n minus r factorial. I'm not going to tell you what this is exactly either. You should know by now. By convention, you take 0 factorial to be 1. Don't forget this. Sometimes you might get a 0 somewhere in your calculation out of nowhere and you feel, oh, I get a 0. But if it's 0 factorial, make sure you write 1 in place. Okay. So the first thing we'll properly review is circular permutations. So suppose I have r distinct objects. So say I have n distinct objects actually. So yeah, here you can, I guess, mention NCR is equal to n factorial over r factorial as well. Again, something I expect all of you to know beforehand. So suppose I have, can no one hear me? I think the rest can hear me, in which case it's not a fault on my end. So suppose I have, yeah. So in case anyone else says that I'm not audible, just ask me to refresh so I don't have to. Yeah, thank you. So suppose I have n distinct objects. And I wish to permute. So I wish to choose first r of them and then arrange them in a circle. And then arrange them in a circle. Fine. So the number of ways to achieve this is denoted by q, and this is equal to npr over r. So notice that ncr had a r factorial, but now I have only an r. Okay. And the case which you are all familiar with is when r and n are equal, in which case this is simply n minus 1 factorial. Okay, the reason this turns out is that you take a circular permutation. So say I have some x1, x2, blah blah blah, xi, blah blah blah, xr, and it returns fine. So this is xi, and there are some more here in between, some in between here, none here, so there's nothing here. Then you notice that if I cut it somewhere, so say I cut it here, then I get a string out. So if you can follow what I'm trying to say, I get something like this, which is just a permutation in a row, which we know can be done in NPR ways. But then you realize that I could cut in r different places, and they would all lead to the same permutation. So you divide by r when you're trying to count such permutations, and that's how you get the formula. Okay. And this was wrong. Oh no, this is good. Okay, circular permutations done. No, so in case the order does matter, it's going to be specifically mentioned in the problem. If not, you can assume that you don't, that you care about the order. If they want you to consider clockwise and anti-clockwise the same, they'll mention it explicitly. Otherwise, you assume this situation. Okay. Fine. So then you have two important principles. So these don't look very combinatorial at first glance, but they indeed are. So let A and B be finite sets a function or a mapping. So let's stick with mapping for now. If A to B is injective, I'm sure all of you know that. If FA equal to FB, or rather A1 and A2, because I took B as my codomain, implies A1 is equal to A2. So if there is an injection, notice that I only care about there being one injection. Not everything needs to be an injection. As long as I can find one, I'm done. Okay, that's enough to satisfy my conditions. If there is an injection from A to B, then cardinality of the set A is always going to be less than or equal to the cardinality of the set B. Okay, this is called injection principle. Should have mentioned it on the top. And then you have the one you will see more regularly, the bijection principle. Okay, bijection. That's good. So I need to define surjection first, though I hope all of you know that beforehand. FA to B is called surjective. If for all B in the codomain, there exists some A in the domain such that Fa is B. So that's a surjective function. F is called bijective. If it is surjective and injective, and in this case, and then the cardinalities have to be equal. So this is what you will use most of the time. So say you have some problem. If you can show a bijection between something you can easily solve and something that's given, then you can use this principle to say that the number of ways to achieve both things is same. So for example, you may have a problem such as choosing non-consecutive integers. Okay, so there is a way to make that problem into one about making binary sequences of some particular length. I won't do the problem now, but this is in Tomato if you solved it. That's one way of doing this one problem in Tomato. And then you can say that there is a bijection between the two situations. So I can solve my binary sequences, which are easier to do and explain. And the same solution follows for that. Okay. This is how you use this. You don't always need to find an explicit function. Just arguing that there exists such a function that is bijective is enough. Okay. Now some standard formula that you should remember. So first let's look at arrangements and selections with repetition. So by repetition, I mean I have my objects are not all distinct. Okay. So first, the number for permutations of D set A1 to AN. So I have some n objects where R comma n belong to n obviously, with repetition allowed. So here repetition obviously means I'm allowed to pick the same object twice. Allowed is, come on, you should know this. n to the power r. Yes. So easy. Then you have another case. So consider a collection of R objects in which R1 are of type 1, R2 are of type 2, and so on, and Rn are of type n, where, so these are all my objects, that is R1 plus R2 plus Rn is my R. Then the number of different permutations of this collection is R factorial over R1 factorial, R2 factorial, so on till Rn factorial. Fine. Okay. Now let's look at distribution. So standard situations in distribution problems. Distribution. So first situation arises when you have R distinct objects. So a standard distribution problem is you have some objects and you have some boxes, some distinct boxes and some objects which may or may not be all distinct. So let's look at the two cases. So R distinct objects into n distinct boxes. Okay, then you have limitations on how many objects can one box hold. So in that case, let's go sub case 1. If each box can hold at most one object, then the number of ways to distribute is NPR. Yes, I'm not going to write number of ways to distribute every time. So that's what I'm going to mention here. That's NPR in this case. Okay. Situation 2 arises when each box can hold any number of objects. In this case, your answer is n to the power of r. And finally, subcase 3 arises when each box can hold any number of objects and the ordering in each box counts. So by this, I mean the way in which you put. So if red ball goes into box 1 and then yellow ball goes, you count that as a separate case to yellow ball going into box 1 and then a red ball going into box 1. Okay. Ordering of objects in each box counts. Does anyone know the answer to this situation? So we had n distinct boxes. No, it's not NPR. And I had R distinct objects. N plus R minus 1 factorial plus n minus over. Did you write n minus 1 or R minus 1? N minus 1 factorial. So that is correct. So the answer is n plus R minus 1 factorial over n minus 1 factorial. Right. Now what? Now you have situation B. Situation B arises when you have identical objects, but the boxes are still distinct. So this is the sort of situation that can arise when you're working with, this, say, eggs, identical eggs in buckets or baskets or whatever. Yes, of course, it is a solution. When you have a lot of ones that you're trying to put into the variables, that's the way you look at it and solve it combinatorically. So into n distinct boxes. Okay. So subcase 1, when I force each box to have one object, that is, there are no non-empty boxes. Or rather, let's start with when each box holds at most one object and come to that one in the end, because that answer is slightly weird. At most one object. So obviously this solution is n choose R only when R is actually smaller than n. Otherwise it would be 0, because you would have objects left over. Fine. Okay. Case 2 is when each box is free to hold however many objects it wants to. So each box holds any number of objects. In this situation, the answer is n plus R minus 1 choose R. Fine. Then situation 3 is the one that I accidentally mentioned first, when you have no non-empty boxes. So that is when each box holds at least one object. Once again, Rishabh, that's wrong. So the answer to this case is R minus 1 choose n minus 1. Yes. And once again, this is only the case when R is greater than or equal to n. Otherwise, you have 0 again, because you will have boxes left over this time, empty boxes, which you don't want. Okay. So a remark here. This also gives you, so case 2 also gives you the number of non-negative integer solutions to x1 blah 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 till xn is equal to r. And one verbal remark I'll make is sometimes the problem asks for positive solutions. And what a lot of people try to do is they work with this formula that gives you the non-negative case, and then they try to somehow find the situations where there is 1 0 involved. They try to get rid of those and so on. And that's not how you approach this problem. So if the problem asks you for positive integer solutions, what you do is you take r minus n instead, and then you approach the problem the same way. So you force all the xi's to be at least 1, and then you arrive at the same situation where you now have n minus r minus n ones left to put in the n boxes. Fine. And then you can use the same formula. Okay. Is there anyone who didn't follow that? I'll repeat it because this is important. This is a very popular type of problem. Okay, so let me write this down then. Yeah, sure. So we know. So I'll go to this previous board once after I do this. Okay, Hardik. So we know that x1 till xn is equal to r. So from this board, this formula, I know that has n plus r minus 1, choose r. Non-negative. This is the keyword, non-negative integer solutions. What about positive solutions? And at first glance, it is very tempting to use complements. So you find all the solutions and then you subtract all the. So you find all the non-negative solutions and then you subtract all those that have at least 1 0 in them. But counting that at least 0 turns out to be a very difficult task. You need to involve things like inclusion-exclusion and blah blah blah, and it's an ugly calculation that doesn't really value it to something beautiful, and it's not a feasible approach. Okay, so what you are supposed to do is, so notice that here I have r identical objects, right? Identical. So let's think of it as having r ones. So just think of one as a symbol for now. Okay, don't worry about the value or that it's a number. So think that you have r ones. So suppose you have some cards on which you wrote 1 on all of them, and you have r many of those. And then how many cards you put in a box describes the value of that box. So, and the x1 to xn as boxes, clearly they are distinct. Then the problem of positive solution becomes the situation where you have to find the number of cases where you have no box empty. So that is, every box holds at least one object, which you know from this situation instead. Fine. Now do you follow? Now does everyone follow? Is there anyone who doesn't follow? Okay, I'll take that as a no. Hardik, where do you want me to scroll? Okay, done then. Last one. So do you mean this thing or do you mean explain that whole thing again? Just want the formula on the board now. Also, you can scroll on the boards yourself. You don't need to ask me. You cannot change boards, but you can scroll on the board that I'm on. Positive solution. Okay, so this is the answer to the positive solution case, case 3. This gives us positive solutions. And the way you reach that conclusion is this. You think of the problem as having r many ones and putting them in n distinct boxes. So you want one in each, that is at least one in each box, so which is case 3 for us. Okay. Okay, moving on. Some properties of the binomial coefficient, basic properties. So first, n choose r is n choose n minus r. Second, n choose r is equal to n divided by r, n minus 1 r minus 1. So here you assume that r is greater than equal to 1. Then you have n choose r is equal to n minus r plus 1 divided by r, n choose r minus 1. Once again, you assume that r is greater than equal to 1. Then you have n choose r is equal to n minus 1, choose r minus 1 plus n minus 1 choose r. And one more, you also have that n choose m times m choose r is just n choose r times n minus r. Okay, so I guess let's wait a minute in case anyone wants to write these down, then we'll move on. Okay, so next you have the binomial theorem. Okay, so for any integer n, so positive integer, non-negative rather, you can evaluate this expression as this summation if need arises. 1 second. Alternatively, if you want me to condense this down, you can write this as n choose I xn minus I by r. I'm sure all of you know this already. Hardik, please try to write quicker if you're writing this down. I really don't want to spend too much time on things that we already discussed. Okay. Yeah. Okay, this is the binomial theorem, and this shows up in a non-combinatorial context most of the time. So this shows up when you're trying to evaluate summations, and you can even use this to find out certain integrations. So sometimes you may want to deduce something by integrating this, or maybe differentiating this, because that can convert this into other interesting looking summations, right? Okay. So now from this you can conclude some more identities. From this you can conclude that this summation has the value 2 to the power n. You can conclude that this summation minus 1 r which is r is 0. You can conclude that summation over where r is odd is equal to 2 to the power n minus 1, and same goes for when the summation is over r even. Okay, then you have a peculiar result that actually shows up in a tomato objective from what I remember. So there's something called van der Moon's identity. And I will not be proving this. You're free to Google. So van der Moon's identity states that a summation of this form I is equal to 0 to r, m choose I, n choose r minus I is equal to m plus n choose r. Okay. So if you want me to expand this, this is just m choose 0, n choose r, plus m choose 1, n choose r minus 1, so on till you get m choose r, m choose 0. So remember this may end up being useful. Okay. And then I guess I can mention one more result here. I can mention that I is equal to 0, n choose I square is 2n choose n. Okay. Now there's something called Pascal's triangle, which once again I'm going to assume all of you know, and I'm not going to draw it. But two identities can be observed from that and can be proven otherwise as well. And these are called Cauchy's identities. For what reason, I have no clue. The first one says that R choose R plus R plus 1 choose R plus N choose R. These are not essential results, but they are occasionally powerful enough to make some calculations very simple. If you don't know this beforehand, don't bother now. Okay, just phase this out of your brain. You never heard this. R choose 0, R plus 1 choose 1, R plus K choose K. This one is just R plus K plus 1 choose K. And you can observe these from the triangle, Pascal's triangle. So the way you do it is you take two, you use Pascal's triangle to evaluate, and you keep reiterating till you reach the expression on the RHS. Okay, and it will work that way. Okay, now one more thing, inequalities involving the binomial coefficient. So there is one that you need to know. So for even n choose 0, n choose 1, so on. So you increase till this thing, and then you start decreasing. And similarly for odd n, you once again increase first. This time, instead of having a unique maximum in between, like you had for even n, you have two equal values, namely n choose n minus 1 over 2, which is equal to n choose n plus 1 over 2, and then you decrease as before. Okay. Fine. So that was the binomial coefficient, and we are going to be very under time today. So we can revisit some results, I suppose. And maybe there's a good problem that I'd like to show if time permits. Okay, so multinomial coefficient, right? That's also true. So I guess before I start this, I want to address some problems and queries from yesterday. So someone asked me if what I'm teaching in class is enough or even UGB. So to that, my answer was, and I'll explain my stand on the situation once more. Suppose there's a problem, and this is a sketch of the solution. Okay, so if the solution goes something like given facts imply some statement A, which then implies statement B, to which you add, rather write this. So plus some known facts, some other known facts, implies statement C, which then finally implies what was to be shown. Okay. Suppose this is how some particular problem is being solved. Then there are two ways that you can go about solving this. Either you can develop enough skills, and that comes by practice, that you start with this, you conclude this, you conclude this, you know these standard results, you imply this, and the problem is done. That's one way of doing it, which is what I am assuming all of you want to do. The other way is that you somehow convert the problem into a more generalized situation. So instead of taking some particular value, you take n and whatever, and then you condense all of these steps into some one very large and ugly and very niche type of formula that you won't really use anywhere else. So if that was your expectation, that those are the formula you'll get in these classes, nope. You're only going to get the basic stuff that you need to know and which is enough to solve everything. I'm not going to do any weird formulas for one very, very specific type of problem. That's a waste of time and energy. Okay. So we want broad spectrum methods to do things. We don't want surgical precision for every single problem. Okay. And were there any other questions yesterday? Let me check. Okay, yes. So someone asked me for cutoffs as well. So what sort of cutoff to expect and how much do you need to solve? And to that, okay, if you proceed a problem as far as you know to statement C and you don't know the complete. Yes, of course there will be. So I'll come to that. Okay, so let's take a break from combinatorics for 10 or 15 minutes and let's set all of this straight, because there's not a lot of combinatorics left to discuss anyhow, so we'll be under time today. That's great news. Okay, so if you say read statement C, but you don't realize that you can conclude this, so you'll probably get 7 or 8 marks out of 10, which is very good. Don't leave these marks just because you didn't finish the problem. Write it all down. If you feel that your approach should work, but you're struggling at some crucial junction, maybe you're nervous and you can't really think about what to do now, or you hesitate, or whatever. Yes, there is partial marking in the subjective section, exactly. Okay, so you want to write as much as you can, as long as it is correct and relevant to the problem. So, for example, last year's entrance. So, okay, sure. Sure. There you go. Okay, so I'll keep talking about what I was talking about. So, I'm assuming all of you have seen 2019's UGB paper, right? So in that, there is a problem where you have to find the shortest distance between two curves. So it's problem 8 in my set at least. I'm not sure if there were other sets with other orders. So it gave you two curves. I think they were hyperbolas, and you had to find the shortest distance between them. Right? Does everyone remember that? I cleared it, so you're in good hands. I can say that much. Yeah. So yes. So in that problem, if you just write that the shortest distance will be along the common normal, then you explicitly find the equation of the common normal, you'll once again get 6 or 7 marks, even if you don't prove or justify that the common normal is in fact the shortest distance. Without even proving that statement, which is more or less the gist of the problem, you'll get 6 or 7 marks. Okay. And yeah, so then there is the question of how much do we need to do. So disclaimer, I suppose, this year is an unprecedented situation. There is no real comparison to be made with any of the previous years where there has been an interview. So since they are going to take top, so I guess I can compare this way, is that every year the cutoff hovers somewhere around 80, and for UGB it hovers around 35 marks. Okay, so this is for this year's entrance, so we are not worried about the interview today. You can attend these sessions next year and then we'll be concerned about the interview. So for UGB, this is out of 120. For UGA, it's 120. For UGB, it's 80. CMI, it's usually around 60% of whatever the total score, maximum possible score is that year. So they keep varying it between 100 and 125. So you can take your guesstimate that way. Okay. 60% is no. This is for a standard year. So this is when they shortlist. So I'll talk in ISI context for now. So this is when they shortlist the top 150 for the interview. This year, that's not going to happen. This year, they're going to straight away offer admission after the written test. So that means they're probably going to shortlist 70 to 80. So you can expect UGA to be somewhere above 80, but I assume below 90. And you can expect UGB to be somewhere around 40 to 50. So this is the year you definitely need to do better in than all previous years. Okay. And I'm not sure about what sort of paper they're going to set this year. It may be a particularly high scoring paper so that they can see oh, there are 50 seats, 50, out of which, so since this is India, you should know there are 25 general seats, 50 total. But usually they do offer in second and third lists, they fill up the seats, they try to fill them up. They don't leave reserved seats empty if there is no reserved candidate. Okay. Let's not worry about that. Do your best. Whatever happens, happens. Que sera, sera. Right? And minimum required questions. So, Navya, okay. So, I hope you still take me seriously as a teacher after this. But I only solved one problem last year. One full solution was all I had, and some partials. But as far as full solutions go, I only had one. And that was the easiest problem in that paper, the one that could be done using induction. So it wasn't a particularly impressive solution either. You can find those on AOPS, I guess. You need to ask people. Those are available on AOPS. I'm not sure what the cutoff was. My rank ended up being 28 after the interview, but I had a particularly good interview. So there's that. Like they asked me two problems in the interview, which I managed to solve in one go each. So I didn't have to take hints or whatever from them, which a lot of people end up doing. Okay, so I guess I'll tell you how the interview went for me. We can do the problems from the interview actually. So I'll tell you what they are looking for when they're looking for solutions through this story. So the first problem that they asked me was, you have a quadratic ax square plus bx plus c, and this is a problem from Tomato actually. Tomato, so we can try it. Right, so they asked me that you have a quadratic ax square plus bx plus c. Obviously, a is non-zero, and b, c, a, b, c are all odd. Then show that the roots cannot be rational. So they asked me this. Now I'll tell you what happened there, which should give you an idea of how they go about looking at your subjective answer script. So I started by explaining that I want to investigate the quantity b square minus 4ac, the determinant, and see if that can be a perfect square ever. Because if it's a perfect square, then the root can be rational. Okay. So then I took a mod 4 test. So any integer x is congruent to 0, 1, 2, 3 mod 4, which then implies that any perfect square is either 0, 1, 3 gives me 9, or 0 or 1, yeah. So then I tested this mod 4 and I got b square. So this equation mod 4 reduces to just b square, which tells me nothing, right? So at this stage, one of the professors in the room, so there were four, one of them was about to ask me why I did what I did and why I think this is going to give me an answer. And my inner gut was saying that this is the case. So when they asked me the problem, they said that can roots be rational? So they phrased it as a problem instead of prove this situation happens. Okay. So I knew that it cannot happen, and I wanted to show that b square minus 4ac is congruent to something that cannot be a perfect square in some situation. That's what I was going to do. But mod 4 didn't work, and this was my bad because I had a 4 here, so I was losing information when I took mod 4. So before I could say anything, another professor thankfully interrupted the other professor and said, let him carry on. And I took mod 8, which will work. Okay, so with mod 8, you'll get a contradiction and that will work. Fine, so that's what they're looking for when they're checking. They're not particularly interested a lot in your calculation and your manipulation of some weird expression. They're more interested in what you think you're supposed to do and what you actually do and how well you execute your plan. So even if you can't solve a problem, if you have an idea, mention your idea in some uh, precise way that, like I said, that I want to claim that the common normal is the shortest distance, and then you find the common normal. But then if you don't prove that claim, they still know that you had the right idea, but maybe you just couldn't take the last step. And you'll get marks for that, good marks for that. So in my situation, I did one problem fully. I left two blank. I was completely wrong in one. So this was totally wrong. I'm sure I got more partials in that. And I got partials in 4, which is where I really managed to clear the cutoff. Right? Best way to prepare. That's obviously just practice. So Tomato is your book for this whole thing for ISI entrance, as far as I know. CMI, of course, maybe it's not enough, but for ISI, Tomato is the holy grail. And you should know this book like it's the back of your hand. You should read the problem and the solution should immediately be in your head. You should have done every problem that many times. You just know. You should know every single case of misprint. You should memorize what problem is what. You should do this book so many times, read this so many times that you memorize the problem numbers. That's the way to go. Of course, keep doing other problems along with it, but this is the first step. You need to know this book inside out. For other problems, you can look at RMO papers. You can look at old INMO papers, not the new ones. New ones are usually tougher. You look at the older IMO papers, so before 2005-6, that time. You can look at some US AMO problems. For objectives, you can look at AMC 10 and 12. So these are American Olympiads. And yeah, and you won't really run out of problems, I'm sure. You're all students at Chinta, so develop a peer group, start talking to people at Chinta. Don't be a stranger outside of class, and they'll have doubts which they'll ask to you, and that way you'll get more problems, and you'll have doubts and you can ask them, and that way they'll get more problems, and so on. Okay. But let's come back to combinatorics for now. And if we are, once we are done, if we have time left, maybe we can go back to this discussion. So multinomial coefficients. Okay. Let n, n1, n2, nm. So we don't really know what this is right now. I'm defining it. Denote the number of ways to distribute n distinct objects if n distinct objects should be correct. Correct me if I'm wrong somewhere. I don't think I am, but I haven't read this in a while. So into m distinct boxes such that n1 are in box 1, n2 in box 2, and so on, nm in box n, where n1 to nm are all greater than or equal to 0 with their summation. I have no clue. I mean, I do know what it is, but you don't need to worry about it. It's some geometry transformation. You can ask that in the geometry class, I guess. Let's not worry about it now. It has something to do with triangles, and I advise not using it. Because you will be tempted to use it in a lot of situations where you'll think it is applicable, but you won't be able to show that the conditions hold. So this is one thing that's going to happen. If your solution is correct, but you don't justify it fully, then they go the other way around. If you write everything without claiming, so if you write something, okay, let's come back to this after multinomial. Remind me to talk about claims, okay, after I finish this. So with n1 blah blah blah, then clearly the value, is just n factorial over n1 factorial into factorial, so on till nn factorial. Okay, these are multinomial coefficients. Fine, everyone follows. Can I move on to another board? Okay. So then you had binomial coefficients, and then you had the binomial theorem. This time you have the multinomial theorem. Multinomial theorem. This says that for n and n belonging to n, belonging to natural numbers, you can expand an expression of this type into this summation. x1 to the power n1, x2 to the power n2, so on, xm to the power n. So now the question is, what is this summation over? So I'll write it down. The sum is taken over all M array or rather just arrays. I hope this is the correct spelling. N1, N2, this is 1, so on till Nm of non-negative integers with their summation equal to n. And this, if you don't already have memorized, you can ignore. For what topic? I don't know what book that is. So name the topic. I can name the standard book that most people use. Algebra. What do you want to study in algebra? There's no need for an algebra book. So don't go out and buy a book on polynomials or something. It won't be what you expect it to be and what you need it to be. Okay. For algebra, if you can get your hands on some JEE study material, that would be best. There's no real book for algebra outside of those that JEE people use. So maybe some Cengage or something. Okay. So if you somehow have this idea in your head that you don't need to prepare for JEE or that JEE preparation is useless, yeah, it's wrong. It's math. Math is math regardless of what exam you're appearing for. Okay. So math doesn't change. That's the good thing about it. Okay, so this is the multinomial theorem, and you can ignore this if you don't already know this. But what you can't ignore is this fact that from there, so let me just write this on this board. So this summation then where it is taken over the same thing is equal to m to the power n. Okay, this result you should memorize. And one more thing, the number of distinct terms this is also sometimes asked, distinct terms in the expansion of x1 plus x2 till xm to the power n is this thing, n plus n minus 1 choose n. Okay. So has everyone written this down and everything? So can I move on? Okay. Okay, so then you have 3 small results which are very useful. So let's start with pigeonhole principle. Sure. Let me know when you're done. Pigeonhole principle. So this says that let k and n be any two positive integers if at least kn plus 1 objects. I mean, PHP is not something you need to actively know. It's something that most people can passively realize without explicitly knowing. That's what happened to me anyhow. I never really thought about this result. If it was the case, it just immediately I realized it. Oh yeah, I cannot have every box with just k objects and so on. Okay, are distributed in n boxes. And then one of the boxes must contain at least k plus 1 objects. So like take the situation where you have 5 objects in 2 boxes. So without even knowing PHP, just a bit of common sense tells you that one of them must have 3, right? At least 3. You don't need the strong form, so don't worry about it. Yeah, don't worry about PHP. I'm sure most of you can just think of it passively. Fine. This just comes to you when you're solving the problem. You don't need to actively hunt for PHP. At least I never had to. I'm sure my experience doesn't generalize to everyone, but still. Okay. Then you have principle of inclusion-exclusion. Sure. Okay. Principle of inclusion-exclusion. This one is something that you should maybe actively search for if you're stuck with some lots of cases and complements going on. So for any Q finite sets, A1, A2, so on till AQ. So just say that Q greater than equal to 2, otherwise the statement is trivial. The cardinality of A1 union A2 union AQ is given by this very, very long formula. So take the cardinality individually, add them, get rid of the intersections. So you need uniqueness, so you can write this here, that ensures uniqueness. Then you accidentally, no, definitely not. And then so on. And the general, or rather the last term, I guess, is this. So intersection over all of them. Okay, and the way you use it in combinatorics is, so you need to realize when you are counting the number of ways to do something, you're actually counting the cardinality of some set. So if I say, how many ways are there to arrange 5 numbers in a row? Okay, 5 objects in a row, 5 distinct objects in a row. Then the answer is just the cardinality to the set of all such 5 tuples, right? 5 arrays. If you don't know the word tuple. So you see cardinality, you can think of it combinatorically. Is everyone done? Hardik, are you done? I don't want to come back to this. An example. Okay, so let me go through one more theory topic and then I'll quickly find an example. Fine. There's just one topic left, so let's finish that. Then we can take doubts, any examples you need, and so on. Fine. And this is derangements. And you don't really need to know a very general form of derangements, just this special case that I'm going to tell you is all you need to know. Let S be A1 to AN be the set, be a set of an object and let I be the correct. So by correct, I could mean any one particular arrangement of these, right? Or rather position. of AI in a given permutation. So you can think of my A1 to AN as being letters and the I representing the corresponding correct envelope, right? Yeah, in a given permutation. Or you can think of my A1 to AN as being car keys and my I being the corresponding car to a given key, assuming that no two cars unlock with the same key, of course. That would be stupid. Then DN will denotes the number of permutations such that no object is in correct position. That is, how many ways can I try to unlock my car such that no car unlocks? Or how many ways can I mail my letter such that no letter reaches the correct address? Fine. So then dn is equal to n factorial over 1 minus 1 over 1 factorial. So this is obviously 0, but you write this for pattern's sake. It's easier to memorize that way. Or you can just start at half, I guess. No problem there as well. Minus 1 to the power n, 1 over n factorial. Okay, everyone done writing this? Okay, waiting. Yes, waiting. Uh, 8:30. So you have a level 5 class, I'm guessing. That's why you're asking, right? Yeah, this will end by 8:30. Don't worry. Today I'll end it before. Fine. Is everyone, in which case is dn non-zero? When do you see dn being 0? There is only one case where dn is 0. That's when n is 1. For every n greater than 1, dn is always non-zero. Fine. Okay. So there are some properties that dn satisfies, some equations. So let me just quickly write those. So there are two recursions. If you don't know these beforehand, you don't need to know these now. Okay. So it satisfies these two, which is how you obtain this formula that I wrote on the previous board. Not really, not anything fancy. You don't need to know any theory or like properly study them. There are some recursions in Tomato, just solve those. That's all you need to know about recursions. Just how to solve those. Gets you a general idea of how to solve very basic problems, which is all you need to know. Recursion is not a specific topic to prepare, okay? Just need to have some rough idea of how to. And one that you should know, so not a recursion. I have no clue what Stirling numbers are. So I'm guessing the answer to that is no then. Oh, okay. I remember now. So now, yeah, these are of two types. It's something like that, right? Stirling numbers of type 1, type 2. Yeah, don't need to know those. No. There are similar things. So there are something called Catalan numbers and Ramsey numbers and Ramsey type problems. And you don't need to know any of those. Okay. Okay. So dn satisfies this limit. Can anyone guess what shows up here? Yes, 1 over e. So a surprise e occurs. Fine, and this finishes the combinatorics review. So now someone wanted an example of principle of exclusion-exclusion in inclusion-exclusion. You can evaluate. I'm not going to bother with that. Plus, I know you are giving entrance next year, so definitely not going to bother for you. Okay, so finally, cardinality is there, right? Even if you don't realize. So if I ask you in this way, if I write my problem in this manner, so say I define A to be the set A1, A2, A3, such that A1, A2, and A3 belong to 1, 2, 3. A1 not equal to A2, A2 not equal to A3, and A3 not equal to A1. And then I ask you what is the cardinality of A, what will you say? Without explicitly writing everything down. This is just asking number of ways to uniquely permutate three unique objects, right? This is just 3 factorial. Yes, that's it. You don't always see the set, but you have to realize that you can speak of it in terms of cardinality. For inclusion-exclusion, so have you seen problems of this type? So Venn diagram problems. And you want to find out the total number of students given some certain areas. Then you use inclusion-exclusion. I'm sure you've seen this. I'll have to find some specific problem. But now, yeah. So this answers your question, right? So this is the sort of situation where you're using inclusion-exclusion. Pi, as it's commonly called, PIE, not the constant pi. Okay. Okay. Now, I don't see any point of telling you hooks now because there's like 16 days left. But I'm guessing there are people watching and attending who are going to give entrance next year. So for them, I can mention the books I used. So for combinatorics, and bear in mind, I skipped a lot from all of these books. So for combinatorics, I used a book called Principles and Techniques in Combinatorics by two fellas named Shen Xuan Chong and Qi Ko Meng. And I think I did like 4 chapters of this. I skipped all that Ramsey number, Sterling number stuff, and I skip a lot of things. So if I feel that this is not something I need to know, I immediately skip. And fortunately, I was very good at deciding what to skip and what not to skip. For number theory, the book is the classic Burton's book. It's called, yes, Elementary Number Theory. Elementary NT by Burton. Once again, I skipped, I think, half the book. So there's a chapter where called quadratic reciprocity and stuff like that. Everything from that point onwards, I skipped. Couldn't care less. Okay, what other topics are there? Calculus. For calculus, you can use I.A. Maron's book for theory, but don't do the problems in that book because it has some very boring problems which are the straight away formula solving problems. I mean, you can solve 50 of those just in your head in like 10 minutes or so. So I.A. Maron's, what's the book called? Is it called Problems in Calculus? I'm not sure of the name. Probably something like this. Yeah, of one variable, of course. I don't expect to know any more than that. No one does. Okay, what other topics are there? For polynomials, don't read anything. You just need to know Vieta's relations and the few basic results I mentioned. Don't bother reading a book on polynomials. For probability, which is a famous topic in you do the NCRT stuff, 11th, 12th, whenever that was. For How to strengthen NT in 50 days. That's not how life works. It's definitely not how it works. You don't immediately become good at something in 15 days. No, I'm not a telemarketer. I'm a teacher. So for conic sections and just coordinate geometry in general, and for complex numbers, for CMI you also need 3D and vectors. You can use JE books, whichever you like. If you go to some coaching, you can use the material they provide. And for regular geometry, to be completely honest with you, all you need to know is everything in the NCRT books from 9th, 10th, 12th. I don't think 11th and 12th have any geometry, so just 9th and 10th, I suppose. Okay, and that is all. That's all the topics, right? Is there anything left? Other topics I'm sure you already know, like set theory and all that, don't bother with books. You find books, you read some advanced things that you don't need to know and you won't fully understand and you will lose confidence. Okay. So this is that. Anything else did I want to say? Okay, yeah. So I asked you to remind me to talk about claims. So there are two ways to approach something. If you write claim and then you state whatever, and then you write proof of claim and prove it, you are done. Okay. But if you just assume your claim is true, if you just state something, so just a statement and conclusion won't get you a lot of marks. If you make a statement that is not a standard result, so if you use some inequality that is not AMGM or QMAMGM, I guess power mean, Cauchy-Schwarz, triangle inequality, and x square greater than equal to 0 for all reals, if you cannot justify it to some extent, you don't get any marks for this. If it's not a standard result and you use it, if you use one of those big ugly formulas that I told you about, you are not going to get marks. Simple as that. Fine. Is not good. Just this is not good. So you need to justify your claims. If you make a statement, claim, or you use a result that is not standard, if it's not something that is common knowledge at that level, you need to prove it or at least justify it to some reasonable extent. Okay? And then you'll get some worthwhile marks for it. And while attempting the paper, I recommend spending. So you need to recognize the problems you can do. That's one thing. So take 5 or 10 minutes, read the whole paper, do some very elementary thinking about it, and then identify the problems you can easily do. Identify the problems you can do with some effort. No. So in UGB there is no negative. In UGA, yes, there is. It doesn't look negative, but it is. So in UGA, you get, okay, it's +4 for correct and 0 for incorrect and 1 for a question that you've left. So for for unattempted, you get 1 mark. So that's essentially the same as saying there's negative marking, right? Yeah. So if you're not sure, maybe don't attempt. Unless you feel like you're at like only 15 solved and then it's worthwhile there is. But you are sure about 20 problems, then don't risk one just to get 21. You might lose 1 mark, and that makes a lot of difference. It's a very close game. So there will be like, if there are 100 people, okay, 100 is not a good number. If there are 10,000 people giving the exam, there will be 5 or 6,000 who are not even your competition. You're that well prepared straight away. But then in the other top 700, 800, the top 1,000 students, the competition is going to be very close. You can just assume that. So MCQ, you might get like hundreds of people who lost out because of 1 mark. And same goes for UGB. You might have tens and 20s and 50s of people because they only shortlisted 500. So I don't know what else to say. don't get in because they didn't write one claim, or they didn't write in school, or they made some uh, ugly calculation and didn't really justify it, or they had a bad handwriting and the examiner couldn't understand what they do. Any of those things could happen, and they are not liable to justify anything. So keep that in mind. You don't want to give them a chance anywhere. Okay. Yes, of course, there will be one for calculus, so limits will be covered in that. Probability will probably just put in the tail end of some other session if there is time, because there's not really anything to discuss in that. You just need to know Bayes theorem, product probability theorem, and conditional probability. That's all. NT will be there, of course. So the next of these sessions will be on the next Thursday and Friday. And of course, number theory will be there. There will be one on number theory, one on geometry, and one on calculus. Okay. Are there any more questions? And once again, I'm repeating, don't buy books for every topic. So if it's a book that doesn't clearly state that it's for high school students, don't buy it. How many of you have heard of this book called Polynomials by a guy called E.J. Barbero? Yeah. And how many of you have tried reading that book? Do you think it's a book about the polynomials you need to know? Nope. It's a book about very higher math. It's a book that you can read once you've done your second year at ISI. And it's like a massive book, 700 or 800 pages or something like that. Okay. So if it's a book that doesn't explicitly say, just revise your notes, whatever notes you've made. I recommend doing only light problem solving now. Don't try any monstrous problems now, and just reduce your study hours as well. So if you've been putting like 6, 7, 8 hours a day, maybe reduce it to 3, 4. If you're someone who's putting 3 or 4, maybe put 2 now. Don't completely stop studying, of course. Keep revising, keep reading, but let your brain relax now for 15 days so that it's peak performance on exam day, right? Any other questions? So it doesn't have to be math. You can ask anything. And I'll end this class at 8:28, I guess. Okay, because there is another Chinta class at 8:30. So there are students who need to do those. What problems? Are you giving the entrance this year? And then just stop. Just keep revising your old notes and keep reading. Do problems from Tomato. Don't worry about any resource now. Even if you've done Tomato, just revise problems in Tomato now. You do something new, you struggle, you lose confidence. We don't want that. Okay, so just go through Tomato and your notes. That's all you need to do now, and hope for the best. Yes, test of mathematics at 10 plus 2 level. That's Tomato. That's what we call it. Everyone calls it Tomato. Yes, now just keep revising Tomato and your notes. That's it. Don't do anything else. Okay. Any other questions? Okay, then. This is all for today. Level 5 students can go to their class. I'll take calculus. I won't take geometry. Everything else I'll take. Varnana, that's what I did, and I don't want to recommend it. So that is what I did, and I managed to get in, but it's not something I can recommend. I won't tell you not to do it either, but I won't tell you to do it either. It's your decision. You should know how comfortable, how confident you feel doing it. So I'll just say that I did it, and I won't recommend it. Yes, I did. Didn't get in the first time, obviously. Yes, of course, no one prefers to do that. Okay, level 5 students can leave. So everyone else, if you want to stay and discuss, feel free to go ahead. Level 5 students, if you have class and that you want to attend, of course, leave. Yes. So, goodbye to the level 5 students. Everyone else, if you have questions, feel free to keep asking. No, I was a student at Chinta for 1 year. And of course, I prepared on my own as well. Yes, I was a student at Chinta for 1 year. Yes, I am. I started my second year. Yes. Oh, no, definitely not. No, you need proof, not cases or examples. You need proofs. Proofs are always general. You don't want to show that it holds for some and you want to show it for all, holds for all and things like that. Okay. There are cases, there are types of problems where just giving an example is enough. So if the problem asks you to prove existence of something, it's enough to show one example where it all works. But most of the time, it won't be that way. Okay. How to manage time in easier. So a similar thing goes again. So read the paper. You will immediately solve like 10 problems at least. Okay. You will have some good ideas about 10 or 15 problems. Do those first and try to do those as quickly as possible. And then spend time on the problems where you feel, oh, I have seen something similar like this, or I have an idea about what to do, and try those ideas and approaches and see if those work. There will be some problems where you might be clueless as well. Don't let them shake you. Just ignore them. There are without a doubt going to be problems which you have never seen before and which will leave you clueless. Just ignore those. They are not worth your time. Any other questions? Weak areas combinatorics. So read the book I suggested. So Shinchuan Chong's book and solve problems. That's the only way to get confident in math. You keep solving. It's the ultimate goal in math is to solve problems and to understand things, of course, but solve. Yes, I did. Only once, though, not in my first attempt. I did last year. Yes, of course. So there's no other advice in math. You keep reading theory, you try to understand theory, and then you solve problems. Okay, keep asking, don't stop. As long as you have questions, keep asking. Once you're done, you can leave the class, I guess. And once I have like 5 or 4 people left only, I'll leave. Okay, no more questions. Okay, we'll only the. Oh no. So they'll put out a list of 70 to 80 people, and then they'll start offering admission from the top down. So they'll offer it to the first 50 or whatever, and then depending on how many people don't accept their seat and how many are left. So how many seats are left after first round allocation, and they'll go on to the second list. Maybe so if after, for example, they offer it to the first 50 people and only 40 accept, then they'll offer it to people who have ranked 51 to 60 for the next 10 people and so on till they are out of seats. That's how it works. Once or they are out of the people they shortlisted. So If they run out of the 70, they shortlisted and there is 2 or 3 seats left. They won't go below 70. So once again, read examples, see how it's done, then try to solve similar problems slowly. Try to do problems that aren't so similar and try those techniques, and you will ultimately get it. Oh, no. 50 for BMath and 50 separate for BStat. So the list for BMath and BStat is different. That's why you have to fill in your preference during your application. So it's a different list. You are not going to be competing against those who have applied for BStat or BMath, depending on what you applied for. You're only applying with. No. So BMath is Bangalore, BStat is Kolkata. No other choice. So if you applied for BMath, it's Bangalore. If you applied for BStat, it's Kolkata. Cutoff differences, yes. Traditionally, BStat has a slightly higher, so like 1 or 2 mark difference. Traditionally, that happens for some reason. I'm not sure why. I am a BMath student. Yeah, it's fine. It's fine. I mean, that's why I'm here, right? Now we know you cannot. Once you've applied, and then after that, they give you like a 2 day window or 3 day window once applications in to change under if you have some special circumstances. Otherwise, no. Once you have submitted your application, you are locked into that choice. So think carefully before you apply if you're applying next year. And this is some advice from my side. If you want to do math, do not go for BStat. That course does not have enough math to justify your interest in math. Okay. If you do want to do math, come to BMath. There's enough career opportunities after BMath. Don't worry about it. There's no shortage of jobs. I ensure you. Okay. And I guess that's all the time we have today. So, are there any questions left? Any important questions that are relevant to your preparation, not my biodata? Okay. So, of course, everyone has to ask this one thing. If you want to do math, go for ISIB math. If you want to do math but you're not completely sure, go to CMI and take an extra subject. So that way you'll have a good background in either physics or computer science, theoretical computer science. At ISI, even though you have courses in physics and CS, so you have 4 compulsory courses in physics and 2 in CS with some electives on offer. But no one really takes those seriously. I mean, outside ISI as well, because your degree still says B Math, not just BSc, it says B Math. It says math right in the degree title. So only come to B Math if you're sure about liking math and want to stay in a math career. If you think there is a chance you might just want to leave math entirely and switch to CS, then don't come to B Math. No, not for you. There will be some ways to still get rid of math in your life, but it's going to be difficult, and you essentially done 3 years for nothing. Okay. But yeah, again, this is like taking a drop. It's up to you. I can't really make that decision for you. In my experience, the faculty at ISI is better though for math courses and a lot more active in terms of their research. But okay, done then. Okay, I'll end this session now. Bye bye.